All right, and our first lightning talk today is Brandon Bennett from Facebook with automated network provisioning.
Good afternoon. My name is Brandon Bennett. I am a network automation engineer at Facebook. And one of the areas that I've been concentrating on for last couple of years is how we can automate the provisioning of our networks. So I'm going to go through a brief history of what we've done so far, and then jump right into where we're actually going and what we've developed to help with some of the problems that we've had in the past. So in the past, I actually looked at the Git history for the service that we've used in the past, and it was actually committed to 10 years ago. And if you can imagine where automation and networks was 10 years ago, there wasn't zero-touch provisioning, there wasn't any of these newer technologies. So how do you automate that? Well, you do exactly what a human does. You get out your laptop, you plug into the console port. So the system was actually based off of that. So we had our provisioning servers, or servers, that would actually SSH into console servers and then screen scrape consoles. We actually still have this running in a limited fashion today. It's amazing that it works the way it does, but you can imagine screen scraping is not necessarily the most ideal way of handling things. We've also ran into a couple other problems the way that this system was designed. It was designed to provision a device in the context of a job. So a job would be kicked off, that would be stored into the database. And then all the provisioning aspects of that device was handled inside that job. And there's a lot of things that happen besides just applying a configuration and applying a config to it. And I'll get into that a little bit more. The other thing that we kind of ran into is, as we designed the system, it was designed to actually handle only top-of-rack devices initially. And that worked so well, we started adding in fabric devices. And that worked so well, we started adding in backbone routers. And you can imagine that if you have this code base that started off as something really small that wasn't planned to be extended to the extent that it was, there's conditionals spread all over it. You'd make one change over here, and it would break something over here. You'd fix that change, you'd break the third device. So it became pretty hard to try to reconcile. It was also very slow, because you can imagine actually pasting in a configuration over 9600 baud was extremely slow. Everything was done very serially. We do this, we do this, we do this. We also did like LLDP discovery during this process. So we would show LLDP neighbors, try to figure out what the device was. And so we needed to solve this. So it's not always a good idea to rewrite something just to rewrite it, but we were actually running into some issues. So if anybody follows Mark Zuckerberg on Facebook, you'll probably notice that there has been a couple announcements for data centers in the last year and a half. So these are 5 new data centers that we're announcing. There's multiple buildings going into each one of these regions. There's a lot of switches that need to be updated for that. So I'm sure everybody out here is actually asking yourselves, why not just use ZTP, right? ZTP just solves this problem for you. Most of the vendors now have pretty good support for it, that it should just work, right? Well, the problem is, like, ZTP is the right base to base your provisioning automation on. The problem is that there's so much more to automating a device than just getting a config and code on it. So code generation is actually a very large part of this, or a config generation. You need to find out, somehow map back that this serial number or this chassis goes to this config. You need to be able to generate that config. You need good modeling for your circuits and for your other device configuration. After you get done applying the code and configuration of the box, you need to verify that the box is ready for service. This includes power supply checks. You've got redundant power supplies, make sure they're both on and operational. This includes optical checks, make sure that your DOM levels, your light levels are good. Fans are spinning, things like that. And you also need to set up alarming and alerts and get your box into your inventory management systems. And usually there's a flag to enable that to go into production. We also, if there's a top of rack device, will automatically kick off server provisioning as well. As soon as the top of rack device is provisioned, go ahead and do the servers next. There's no reason why that needs to be a human to come in and do that. And the other thing is ZTP only handles the initial configuration of a box. There's other lifecycle operations that we need to be able to handle. That includes upgrades, reconfigures, like complete reprovisions, and decoms as well. So we needed a system to kind of handle all this. So ZTP on itself, that little blog article on Arista's website wasn't enough. So here's what we came up with. It is a ZTP-based solution. So we started off with that. We already used the Kia DHCP servers for Pixie booting our server environment. So we're able to hook into that. Kia actually allows you to have plugins written in C++ that hook into our backend systems. So we could actually assign the real IP address directly to the box, the real management IP address that it would have anyway. And inside that DHCP offer message that comes down to the box, unfortunately, this is only IPv4 at this point. In that offer message, we actually, instead of providing a configuration to be applied to the box, we actually download a Python agent, or a little Python script that we call an agent. And the reason why we do this is there's not a whole lot of visibility when it comes to running ZTP on a box. You plug it into the network, it runs stuff. If you're plugged into the console, you can see logs scroll by, but that defeats the purpose. So we have this little agent that will actually look at the logs coming off from the ZTP process, and it will stream that off to this gateway. It will also find out exactly what files need to be downloaded and what config needs to be applied, and in what order. We sometimes also write software that runs on these devices, so we need to download those RPMs or download those packages and install them at this time as well. The ZTP gateway is just a really simple REST gateway. The reason why we're using REST at this point, we're not a big REST shop. We don't use it anywhere else. The only reason why we're doing it here is because we want the agent to be extremely lightweight. We don't want to try to package third-party dependencies. HTTP clients are part of the standard library in Python, so it's very easy for us to just utilize URL-lib in Python for that. Then there's actually a controller that kind of controls the entire job. This is really the interactions with the database so that we can log, to insert the log messages into the database, as well as the current status of the provisioning job. And then for all that other stuff that is not covered by ZTP, all the audits, all the checks, all the additional steps that we need to do after or before provisioning starts, we created this this queue-based system where we actually split everything up into steps. We utilize Zookeeper, Apache Zookeeper, to create a simple queue, and then we have a number of executors that actually run these steps as they come in. So it's a simple job queue system. Really quick on the steps, we really looked at having one big, what we came from, which was having this one big binary that had a bunch of conditionals in it that kept breaking. The blast radius was huge. Every time we had to make a change to our provisioning system, we risked taking down provisioning somewhere else, and this was happening too often. So we actually really wanted to solve that problem here, and we created steps as really small standalone programs. For the most part, these steps are less than 200 lines long. They could be written in any language. We actually made the steps where they're just an executable that takes in input from standard in and outputs logs in standard error. So it's, we can plug in whatever we need to do. So as Facebook needs to change to different directions, we can do that. And then we wanted them to fail really, really fast. If there was a problem, we wanted the program just to exit with an error code that wasn't 0, and then allow the system to automatically restart. There was a lot of instances where we would fail an entire provisioning process because one little thing was wrong. A good example of this was power supplies. We'd have dual power supplies in a box. We were doing the checks way at the end of a job, so we're putting on a config, we're doing all this work, and then way at the end of the job, we're checking for power supplies. Whoops, one of them's not plugged in. Fail the entire job, start over from scratch. That wasn't working for us anymore. So now we can do power supply checks and retry them over and over again. In fact, we can retry forever if we wanted to. Or we have another option where we can bypass one of those steps. Bypassing it will actually open a ticket in our ticketing system to somebody actually to, I guess, automate the humans, as I put it, to go take a look at why that power supply is failing, but still allow the servers to be provisioned after that. So don't block us on that. And then we can define what steps are being ran based off the role or the actual model that we're, the hardware model that we're actually operating against. And so finally, I just want to say thank you for having my talk. Here is my team that put this together. This is actually at our Ireland data center that just got turned up this summer. As you can imagine, they're still doing construction as we were provisioning devices with our new system. Thank you very much.
All right, thank you, Brandon. Up next is Joel Jaeggli, and he's going to talk about flow label hashing in IPv6.
All right. Blame for this talk belongs to me. However, I have coworkers, and they're actually largely responsible for the success of this little project. There's also one other person who needs credit, and that is an anonymous Debian user. So if we start at the beginning, RFC 18883 actually defines what the IPv6 protocol specification looks like, and it includes the structure of the new IP header. In the new IP header, there's a 20-bit field, which is known as the flow label. So what do you do with this? Well, the idea originally was that you would build new routers that utilize flow caching once you've identified a flow to speed up forwarding lookups. On the left-hand side, you see a circa 1969 to 1989 packet switch. On the right, you see a modern one. Packet switches are actually bounded by the worst case forwarding situation. In the right, that's less than 1,000 packets per second, or on the right, and it's 5 billion. Okay, so what happens here? RFC 1883 is pretty unequivocal. All packets in the same flow must be sent with the same source address, destination address, priority, and flow label. That's pretty clear. Unfortunately, we didn't exactly stick with that. About 2011, we came out with an effort to rehabilitate the flow label, and we said a node that forwards a flow whose flow label value in arriving packets is 0 may change the flow label. May? What kind of sociopath changes the flow label of packets in flight? Well, it turns out it's us. But we also said a forwarding node must either leave a non-zero flow label value unchanged or change it only for compelling operational security reasons. Okay, so that basically gives you a license to do whatever you want. Okay, so we have hashing problems because we actually need to distribute incoming flows among multiple servers. We need to do this statelessly for scale reasons, and so we're actually sort of concerned about being able to do the same thing in IPv6 as we were in IPv4. Okay, so this is an actual flow. The first packet that you see there is a SYN. The second packet is the ACK from the same device. There's an interesting problem there, and that is that the flow label is different. The third packet is also from that device and is a TCP reset. It has a different flow label as well. Okay, so here was the initial flow label. This was received on a SYN. This arrived on one server. We replied with a SYN-ACK. And then we have a small problem. Okay, change. Okay, we got an ACK back. This arrived, inconveniently enough, on a different server. You know, if you look at the transport semantics of this, this has the same source and destination, source port, destination port, as the previous packet. Inconveniently, though, it had a different flow label. Okay, this was a reset. So this was actually in response to us sending a reset towards them. They sent us another one, different flow label as well. And the reason this, as it turns out, is because the firewall in between the original sender and us had already forgotten about this particular flow. Okay, so This was actually discovered by a Debian user in Portugal. Debian users are great because they have a tendency to be able to send you PCAPs when they encounter problems, which is quite unusual for end users. You can see that this machine actually sent 2 packets with the same flow label. Okay, who's responsible for this? Well, CPE that belongs to an ISP in Portugal, which is actually quite popular in France as well. Some people ship these things IPv6 enabled by default. It turns out that if you also enable QoS, they have a tendency to change the flow label. Okay, so who is actually responsible for this? ISPs. You know, we kind of did this to ourselves, and in our zeal to deploy this, we've actually come up with several variations of this over time. Flow label 0 was quite common for a very long time. Linux systems are sort of notorious for that until they got beyond that and actually started creating them. We've actually seen other devices do this in the wild, so this particular one was not exactly unique. And that's not on the 20-second timer. Can I make it go forward? Okay. Turns out there are some devices that are in your data centers that may actually be using the flow label as a hash component and you don't know it. I had a particular variety of switch where that was not visible until one probed around in the ASIC with the SDK. It turns out that problems with large-scale projects like the deployment of IPv6 have kind of a long history. We're kind of talking past each other with respect to what we expect protocol implementations to do, and the more times we add options, we get to this particular situation. It turns out you can put anything you want in a dumpster. There are some things, however, if you mix them together, are kind of combustible. We had to remove the flow label as a hashing component from our systems. And you know, when we look at vendor implementations, obviously we sort of demand visibility into what is actually being used as hash components. You know, the question of what it is that you can do with the flow label actually comes up kind of frequently in you know, the context of our industry. My recommendation, let's see if I can get this to advance. Don't do anything. If somebody recommends that you do something with the flow label internally, I would encourage them to find a nice beach. Because if you do something internally, undoubtedly at some point it will leak, right? Or other people will do it. The best thing that we can do actually is to stop creating advice for it and actually pretend like it doesn't exist. That is actually the option that has the least amount of damage to be applied in this case. And with that, I am done. So if there are any questions. Excellent.
Thank you. And up next is Christian Kaufmann, Akamai ICN, or I think Akamai gets a network, right?
So, hi, I'm CK, I work for Akamai. Last year I talked about, in the lightning talk, how someone took over my Facebook account and posted cat pictures. We're not doing that today. Today we talk about the worst kept secret for the last year, also known as ICN, or as other people said, what is Jared doing the whole day? Let's see if we find out. A short recap, as you might know or not, well, Akamai is a highly distributed platform, right? We are CDN, 130 countries, all of that kind of stuff. And what we told you guys for all these years is that we act on islands. So all the clusters we build are islands. They don't have a backbone. We put a certain amount of servers either on it or at an IX, depending on how many we need for that particular region to serve the eyeballs. And then this is a standalone cluster. Sometimes we had situations where clusters for various purposes were actually in the same data center. So you had a row with 10 racks of servers, and there might have been 2 or 3 different clusters for different purposes, but they never talked to each other. Whenever the clusters actually either would have to talk back to the mothership for monitoring or billing purposes or to fill the cache with the content in the first place, then they used the internet. So we gave them transit, and this is how they talk to each other. Over the time, depending on the products we had actually more and more clusters talking to each other. We call that mid-crest traffic, and that traffic was growing. As you all know, when you use transit extensively, then you might run into things where your ISP has tromboning issues, he filters, or two providers depeer each other. So the mid-crest traffic we had when they either talk to each other or for the cache fill was actually often, or once in a while, impacted by these problems, as we all know them. Also, an interesting point is if you actually have clusters which want to now talk to each other, then when you use the internet, then you have exactly the feature set like everyone else. So latency, MTU, or if you provide a highest IPv6 or not the one you're using, all that actually tells you how many features you have and what you can do with the clusters, because you're not in control over it. So, what did we do? Well, we built a backbone. So the ICN stands for Intercity Network, and it connects Akamai deployments together. So this is for the mid-crest traffic I talked about when they have to talk to each other. Usually these are clusters which are at I-axis or in carrier-neutral data center. This is not the ones you have in your network, so we didn't go to your data center and connect them secretly. Then we started to connect them together with the ICN. This is not very different than what a Facebook, Microsoft, Google did with their own backbone for their own purpose, to transport own traffic between your own equipment. So as we have more and more services and where it makes sense, this ICN will then also transport various other kind of traffics between our own infrastructure. What will it not do? Well, we are not building a ISP transit network. So the idea is not to sell transit, any kind of layer 3, layer 2 VPNs, or what are classical telco and ISP products. So this is not the point. The idea is also not to compete with the partners and the peers we have. So we are a CDN, that part hasn't changed. We also have no ambitions to become a tier 1, and whoever thought about that they can buy voice minutes from us next month, it's also not happening. So, why did we build it? Actually, it was the other way around. Like in the last 5 or 10 years, the question was usually, why do you not have one? And one of the main reasons was that the platform was really very distributed. And we didn't have a compute platform per se, like one of the others I mentioned before. So the traffic came usually from the origin server to one of the clusters and then was sent out to the eyeballs. So it made never really sense from a financial or technical perspective to actually build one. With the increased mid-crest traffic, this has changed. So one of the biggest reasons was financial reasons. We had actually cases where we delivered a bit, and before it was going over boundaries of transit where we paid for 5 or 6 times. Bounced between different clusters before it was sent out at the end. So now when you can deliver it yourself, you can see how you not just have an impact on the performance, but certainly also on the cost. It turns out when you're actually having a backbone and you start talking about it internally in the company, then everyone figures out that they have use for it. So more and more departments actually figured out that this is a great idea and what they want to do with it. So you get actually more and more traffic on that. It also helps with traffic localization for end users. And now, as we can have an impact on the cache fill, we can actually optimize it, because now we can pick up the traffic ourselves and transport it for the clusters which are connected to the caches. There are a couple of benefits for you. For the ones which have a cluster, an ANP, an on-net cluster in their network, then now some of the cache fill could, instead of via transit, if you peer with us, come from the ICN network. The other big part is for the people who peered with us, and this is probably the biggest difference. Usually you transported it to the cluster where we then have sent out the traffic, right? So the transport was on your backbone. Now, as we can peer in various cities and various locations, we can actually pick it up where you source it, where your data center is, where the origin is, and then transport it for the ones which are connected to the backbone ourselves to that. So you get rid of the traffic much earlier. That's how it looks like. So technically speaking, there are actually 3 backbones. On the left side, the US, the 9 metro areas, which you might know. In Europe, it's currently 4 cities. And in Asia, if you actually want to call it a backbone, it's a city link between Tokyo and Osaka. This part is already online. So it actually transports traffic since 2 months. And as time goes, we will add more and more cities and upgrade these locations. Before the first question comes, what is the speed and what is the bandwidth? So we decided to actually not even bother with 10 gigs and started to with 100 gigs straight away. So all of these links are 100 gigs or multiple in the future. We have multiple phases. 2 of them are interesting to point out here. So phase number 1 was the mid-crest traffic I talked about, the clusters which talk to each other. And then you get the cost and the performance parts. So that part is complete. What we are now doing is we actually will add peerings to it and help that we get the origin fetches instead of via transit or via the various peering nodes which we had in the past, but where they were not connected on the ICN and then transported. We will, in 2018, depending on what the traffic levels are, starting to connect the 3 continents, most likely Europe and the US first, because that's where the bigger traffic levels are. And then, as traffic grows, do the usual stuff. Bandwidth upgrades between the existing cities, and the cities you have seen were just the start. So we will add, as soon as it makes sense, more and more cities, especially Europe. You can imagine that we will not just be limited to the 4 I have shown. So, and with that, you might have a rough idea what Jared was doing in the last couple of months, or the rest of the team, for that sake. Here we go. Hello.
Hi.
How are you?
I just shared our map with you because we got one too. You forgot us. But Dave Temkin, Netflix. It's interesting. I sent this to my boss, who was involved in a fight when we first started building our backbone. Around, basically, we were told from way up high, actually, there was a specific quote when I came back to Netflix, which was, Temkin doesn't think he's building a network, does he? And of course, now we do have a global backbone. My boss said it best, though, and it's earlier today. The reason why we have to do this really is because the internet is a concept, not a thing. And that at the end of the day, if you need to operate a global network like Akamai does, like Netflix does, you can't have all of those features and reliably know that they will exist across the entirety of the internet. And so to your point, I think that's, I think what you're doing is absolutely the right answer. But if you're operating a content delivery network and you need those kinds of localization features, i.e. you don't want to worry about moving traffic, say, from the US to Tokyo, building a network is absolutely the right way to go.
Thanks. Good. Thanks a lot.